Today we will cover how we can use these LLMs for modeling long context. We will see some changes in the attention, some changes in the position embeddings that will enable us to use these LLMs for longer context. Okay, but before that, can anybody think of what the problems would be if you encounter long contexts for LLMs? What kind of issues would one face? So let's try to think that you're trying to train on entire code base which has like millions of tokens. You're trying to do inference on top of it. You're trying to find out whether there's a bug in a particular code base. So what kind of issues would one face with yeah, very high inference time, right? Because especially what would be the most costly operation over there? So the basically the attention computation. The attention matrix is a n by n, where n is the number of tokens, right? That is the issue that we'll face, and we'll try to see how to deal with that issue in this presentation. Okay, so this is a rough agenda of what I'm planning to cover today. Basically, we'll talk about why we need long context, the challenges with dealing with long context, and we'll look at some papers that have tried to address the problem of long context. Recently, many of you might be aware that Gemini 1.5 released, not recently, a while back, basically an LLM that can handle 1 million tokens in production and probably around 10 million tokens in research. So this is a very active research area, and lots of people are working trying to make these LLMs deal with very long contexts, and we'll see some of the solutions that people have looked at. So first of all, what are the challenges that one goes about? We mentioned one of the biggest challenges. There is this n cross n attention matrix computation, and that is very expensive. It's expensive in terms of memory, and it's expensive in terms of compute time also. So Yatin and I think Professor Tanmoy also have covered flash attention, I guess. So what does that solve? Which problem is it able to solve? Is it able to reduce the computational time complexity, or is it able to reduce the of attention matrix computation? Or is it able to reduce the memory requirement for computing this attention matrix? Time computation, it does reduce time computation because there are a lot of things that are happening, but it does not do away with the quadratic time computation. It's still quadratic in the number of tokens. Memory wise, it becomes linear. It allows it by dividing the queries and the key into blocks. It's able to reduce the time to linear for not the memory to linear, but the computation time still is quadratic. Although it becomes faster because of other efficient introductions in that. Okay, so let's look at that. So memory is, so let's look at, first of all, why is long context desirable to us? As I mentioned, if you have a huge book and you want to summarize that book, entire Harry Potter book, and if you give it to an LLM, it won't be able to summarize. Right now, it has been trained on all the tokens, so it can summarize it. But if it had never seen that book and you try to give the entire book to an LLM, it cannot summarize it. It does not have that big context, right? And similarly, if you want to generate an entire book with a particular storyline, it cannot do that. But more importantly, if you want to do inference over long videos, you have let's say tens of thousands of frames, and each frames has around, let's say you have 100 tokens per frame, then it's basically around 1 million tokens, and you cannot do inference over such a long video with these LLMs that can use 2K or 4K context length. Similarly, for code bases, these the code bases that are there in companies, they're pretty big, right? And if you want to find out how to solve an issue in this code base, these small language models won't be able to achieve. You can something, you can do RAG. You might have seen RAG, where you retrieve some portions of the code and try retrieve some document and try to edit that, try to make changes based on that. But if you want to feed the entire code base as is, you cannot do that. And as I mentioned, the RAG setting. So in RAG, generally, you require that the retriever should be good enough that the top 10 documents that it retrieves should contain the answer. Otherwise, there is no way. I guess RAG has already been covered, right? So you'll be aware that. So what is RAG, first of all? You given a query, you try to find out the documents that are relevant to the query. and you put that in the context window and try to answer the query based on those documents. So if you have a query and in a retrieval augmented setting, given a query, first of all, what you do is you try to retrieve 10 or 20 documents from some corpus, put those documents inside your context window, and then use the query to answer from those documents. What will happen if the document that contains the answer is not present in those documents? Basically, it won't be able to answer, right? So you require that the retriever should be good in order for RAG to work, right? But if your context window is large enough, maybe you can feed thousands of documents into the context window, and then you don't require the retriever to be accurate, right? And also, probably you won't require fine tuning on your task specific fine tuning for the model. You can simply feed all the examples, all the input output pairs for the task. Let's say these are some task specific input output pairs, and you can simply feed them into your LLM and just do in context learning. You don't need to fine tune the model if you have a very large language model, very large context window. Okay, so we have looked at why is it desirable to have a long context model. The question is, why is it a problem? Why can't we just instead of having a 4 context length, let's make it a 400k context length for llama models and just train it. So the biggest problem, basically, if you try to increase the context length, everything increases. But the thing that blows up the most is the self-attention computation. So suppose you have a sequence of n tokens, and you want to compute you want to compute an attention matrix for these n tokens. So how will the attention matrix look like? You will have n key vectors and you will have n query vectors, right? One key vector for each of the token, and similarly one query vector for each of the token. And so totally you will have n cross n attention computations required. So this blows up very easily, right? If you have, let's say, 1 million token, this will be of the order of, so if you have 10 to the power 6 tokens, the number of computations will be approximately 10 to the power 12, right? And this is what we will try to address. We'll look at some approaches that try to address this in the rest of slides. Okay, so I'll cover 4 different approaches. The first one tries to decrease the computational complexity of attention, whereas the remaining do not look at from the computational complexity, but they do not deal with that, but they try to see that how we can use LLMs that are trained for with smaller context, but we want to do inference using longer context, right? Like if you have a llama model trained on 4k context length, how do you use for 32k context length? That's what the rest of the 3 papers, rest of the 2, alibi and position interpretation, will look. And finally, lost in the middle, we'll talk about problems when these can these language models even focus when you have a long context? Can they find out the correct information, correct position of the information in a long context? That's the last paper. Okay, so let's look at how to decrease the computational complexity. So you have n tokens, and so what LongNet does is that it segments these n tokens into n by w segments, and each segment has a length of w tokens, right? So this is one segment, and then each segment computes its query, its attention matrix independently. So for each segment you have key vectors, and similarly for each segment you have query vectors, right? And each segment computes the attention matrix independently. So now earlier the cost of computation of the attention matrix was order of n square, where n is the number of tokens. Now given there are sorry, how many n by w segments, so what would be the cost of computation? Since each of these are computed independently, this will be w square for this, w square for this, w square for this, and w square for this. The total cost of computation will be number of segment times w square, which is order of W. So it's assuming that the length of the segment is constant. This is linear in the number of tokens. So this is a very simple idea, and some version of it you might have seen in long form. Professor Tanmar talked about long format, and this is also based on a similar idea. Now, this segment level attention matrix computation is further the computation complexity of this is further improved by introducing dilation. And in dilation, what is done is that not every token does not attend on every token. So if we say this is T token 1, token 2, token 3, and token 4, and let's say this is also T1, T2, T3, and T4. So T2 attends on itself and T4. Similarly, T4 attends on itself, T2 and T4, and all the other values attention are not computation, and attentions are not computed. So basically, you have a much smaller attention matrix to compute, and how many positions you skip is determined by the sparsification factor. So in this figure above, the sparsification factor is 2, which means that every second token is attended on. So now if you do this, the cost of computation is further reduced. And what would be the cost of computation now? Can anybody think of what would be the cost? So let's look at how many segments we have. We still have n by w segments, and now basically you attend not only w by r is the length, w by r is the number of tokens here. So w by r square is the cost of this computation, and so this would be the total computation cost will be order of n w by r square. So the more you sparsify your attention computation, the cost will drop even further. Okay. Now all this we are doing segmentation, we are doing sparsification. Can somebody think of problems with this? Why is this problematic? And are there any some obvious problems here? The segments will never, if they never talk amongst each other, then how is the information even flowing? It's like independent blocks, right? So you want the information from one segment to flow to the other segment, and achieve that. What is done is that, okay, before we go into that, this is what the conditions look like. By the way, you have this sparsified dilated attention matrix computed here. Q is the query of the after sparsification query vector, and K is the query vector after sparsification. You get the output vector from this. So this will give you the output vector of only these two tokens here. What do about the output vectors of the remaining tokens? So these you can get, right? Let's call this as A11. So these A11 you can fill here, and similarly A12 you can fill here. And using this attention matrix, you can compute the output vectors also. But for the remaining places, for the remaining tokens, the outputs are simply filled with 0. You simply replace it with 0. So here, this final output vector that you get will have some of them zeros in the vector. Yeah. So as we discussed just now, that if we just divide it into segments and don't allow any interaction between them, it's basically same as training individual segments. So how the way this paper deals with this problem is that they use various segment lengths and various sparsification rates. For example, in the for the same set of sequence of tokens, this first attention matrix that you see uses a segment length of 4, right? This is a segment length of 4, and there's no dilation, there's no sparsification whatsoever inside within the segments. In the second attention matrix, the segment length is 8, and your dilation rate is 2, that you are skipping every second token for the second. And in the third attention matrix, you have a segment length of 16, and the dilation rate is 4. That means you are attending only every 4th token. You're skipping basically 4 tokens at a time, and you compute the output matrix using this segmentation. This will, let's call this, that this gives you OR1W1. Similarly, you compute the output vector using this attention matrix. This gives you OR2W2, and this attention matrix gives you OR3W3. So you compute the outputs using each of these 3 different attention mass, and then you sum it up, sum all the outputs that you get, and that is the output for one token. So the output is not of a token is not just computed using one segmentation sparsification, but a mixture of segmentation sparsifications, and that allows. So this the output that you get here will look at only local tokens. So it will focus more on the immediate requirement, like after I say he, the word is or was should come, right? So these are local requirements. So this attention allows you to look at that locally what token can I predict here. Whereas if you look at this last attention matrix, this allows the tokens to focus more on global level information, like where should I mean, if suppose a token depends on some information that was present 100 tokens far away, this attention matrix allows you to look far apart, and so you combine the outputs from each of these attention matrix, and you get a mixture of local and global information. And how do you combine the information from each of these 3 different attention matrix? So if you, let's go back. So when we computed the output, there was a soft between query and key, and we use the denominator of this softmax to weigh each of the outputs. Yeah, so S1 is the weight of the softmax, weight of denominator of the softmax for the first output, and Sn would be the output of denominator of the softmax in the nth attention matrix computation, and combine all the different outputs. But does this make sense to anybody, that combining the local and global information? And what is the advantage? So here, this part is expensive, right? You are trying to for each segmentation and dilation rate, you are trying to compute the output. So you're repeating the output computation within a layer multiple times, but it's still less than the quadratic time it would have taken if you computed the entire attention matrix. So you're still not computing the entire attention matrix. If you look at this attention matrix, this is not quadratic, right? You're still but by choosing your segment length and dilation rate, you are able to combine information from both local and global. And this shows the time required for longnet versus vanilla attention, which is quadratic in n. And as you can see, as the context length increases from 8K to 64K, basically time blows up from around 300 to even around 6,000. So time blows up 20 times as you increase the context length by 8 times, right? And whereas for dilated attention, the time remains constant. We can approximately constant. You can choose your segment length and your dilation rate so that the time remains almost constant or linear. You can based on your choices, you can vary the time required. Okay. Now you're still required to train with the data with long context length. Why? Because we have not talked about that. Okay, that's, and the problem with training with long context length is you have to compute the embedding of each token anyway, right? So it's anyway time is going to be linear in the number of tokens. So can we now something else? Can we actually train with shorter context and do inference with longer context? Maybe train with only 2048 tokens, but during inference we give it 32K tokens, and is that even possible? So that's what we will look at in the next few slides. So let's go back to our aim. So what we want right now is that we want to train with, let's say, 2K tokens. We want to do inference on using 32K tokens. What can be the problem if we do that? Let's say if I take a GPT-2 model that I was trained using 1K tokens, and I try to do inference and try to give 2K tokens to it, what kind of problems will we run into? uh, let's say you give let's say you take a model which uses sinusoidal embeddings, sinusoidal position embeddings, right? You can generate a sinusoidal position embedding for 1K tokens, 2K tokens, but will the model be able to use those sinusoidal embeddings now? Because those sinusoidal embeddings are never seen during training. So when you give those new sinusoidal embeddings to the model will go haywire. uh, so the problem that happens when you try to use more context than that was given during training, that one of the biggest problem is the position embedding. The position embedding, whatever you trained on work, but if you try to use position embeddings that you did not train on, it gives a problem. So that's why let's look at take a quick recap of position embeddings. So what is a position embedding? Transformer is mostly a set level operation except for the addition of the position encoding part. So at the beginning of before you feed it to the tokens to the model, you associate a position with each of the token. Like if you're saying I am a student, so this is the position 0, 1, 2, and you somehow encode these positions uh, here and add it to the token level embeddings, right? Similarly, you will encode 1 somehow and add it to a token, and you will encode 2 and add it to your token, right? Uh, and because the model has never seen the position level embedding of it, was trained for 1024 tokens, so it has never seen the position embedding of 1025. And now if I add 1025 to a certain token, the position embedding 1025, it goes haywire. And so what we want is a model that is able to deal with longer context than it was trained on, that it can without the problem of dealing with these position embeddings. So this was an experiment done in the Alibi paper, where what they did was they took these models, we use sinusoidal embeddings. Sinusoidal means that the positions are some sine cos functions of the position embeddings are sine or cos function of the position, right? So they took the sinusoidal embeddings for the position, the models that use sinusoidal embeddings, and they trained on 1024 context on Wikitext with 247 million parameters. And what they observed was that the perplexity during inference was around something like 20. Now they try to increase the number of tokens during inference time. And as you can see, so generally, what do you expect? First of all, generally, if you provide more context to the model, its perplexity should drop. Why? Because there might be some information that you could not give in the 1024 tokens. If you give more number of tokens, the model should be able to do better reasoning. Its perplexity. Perplexity basically the level of surprise. Surprise level should decrease. But when they did this, when they gave more tokens during inference, what they observed was that the model became more perplexed. The perplexity actually blew up drastically as soon as they as soon as they moved from 1024 to 1025, the perplexity started increasing. So the model did not generalize in terms of positions at all, right? And they repeated the experiment with the rotary embeddings. Uh, and again, the perplexity started increasing as soon as they increased the number of tokens. And with T5 bias, also the perplexity initially dropped to some extent, so it was able to generalize to some extent, but then it again started increasing. So they wanted a model which they can train on 2048 tokens or 1034 tokens, still generalize much beyond it. So how do you do that? So the core idea was, so this was their idea, the Alibi idea, which ensured that the perplexity went down slightly, but it never increased. It may or may not have improved. The improvement in terms of performance in perplexity may not be a lot, but at least it did not increase, right? So the core idea was to actually get rid of the position embedding altogether. That adding the position embedding is causing this loss of generalization. So let's get rid of that. But if you get rid of that, what would happen? If I don't give the position embedding at all, what might happen? Yeah, you won't. The position information is lost, and now basically the network is looking at as the tokens as a set. So basically, whether you say the cat is running from the dog, or the dog is running from the cat, or the dog cat running, whatever order you give, it's the model cannot differentiate between these set of tokens, right? So position information is needed. Position embedding, but you still want to get rid of the position embedding, and so the idea was, let's put the position information in computation of attention. When you are computing the attention, uh, the model can give more attention to the tokens that are closer to it and less attention to the tokens that are further away from it. And let's, so as I mentioned earlier, we had token level embeddings, we had position embeddings, we added them together to get the embeddings with position information. Now Alibi removes this position embeddings altogether, and you don't have this now. And the position information gets added to the attention matrix. So this is how a typical attention matrix looks like. And you compute the query vector for each token, you compute the key vector for each token, and compute the inner product, do the inner product to get the attention value. This is how a standard attention looks like. Now the core idea was that when I am computing this attention between query and key, let me modify this so that if you are attending on close nearby tokens, the attention is higher, and as you move away, the attention gets lower, which is somewhat mimics how humans do, right? We when we are trying to say a sentence, my immediate attention is on the token that that I just said, right? After saying I have to say am. I cannot say is. So there's strong correlation in the nearby tokens, right? So the idea was very simple. That let's create an action matrix which is simply m minus n or I minus j. Let me say it I minus j, where I you have this triangular matrix which computes the distance between the two tokens, and you multiply that matrix with m. And what is m? M is just a scalar, a linear factor that basically decides how much you want to decrease the attention. So suppose you want that, okay, as soon as I go beyond 2 tokens, my attention should drop drastically. Then you can keep m large. Or if you want to say that I don't want the attention to decrease drastically, but I want the attention to decrease drastically after 1,000 tokens. Then you can keep m very small. So basically, if m is large, your context window becomes very small, because your attention value will immediately become minus infinity or become very low, right? You won't be able to attend beyond certain width. And if m is small, you can attend to a longer width. Now ideally you want a mix of everything. You want to attend locally, but you also want to be able to attend globally. So what these authors did is that you have multiple attention heads, right? In transformer, they decided that let's use different value of m for different heads. Some heads might attend only local. So for them, local attention means the m should be large. So if some heads want to look only locally, then we can keep m large for them. And if you want to look more globally, the m should be small. And now you will add these positional differences and with the product between query and key, and apply softmax. So if you can see, right, if this distances become very large, then the value here will become very negative, like minus 100 or minus 1,000, and the softmax will go to zero, right? So as soon as the tokens are very far apart, the attention drops to 0. So as I mentioned, since you have multiple heads, you can use a different value of m for different heads. So this m, for example, for head 0 here, the m is defined as 1 upon 2 to the power 8 by n, and n is the number of the context length that you have. So let's say, oh wait, n is the number of attention heads. Sorry, yeah. So if you have 8 attention heads, this m will be n is equal to 8, implies m is equal to 1 by 2. Here n equal to 8 implies m equal to 1 by 4. Here n equal to 8 implies m equal to 1 upon, and this becomes m equal to 1 by 2, right? So this head n has a m set as 1 upon 2 to the power 8, so it can focus on 2 to the power 8 tokens without much drop in the attention scores. Attention scores remain not change drastically, whereas for this the attention head 0, the attention scores drop as soon as you go beyond 2 tokens. Okay, so this is a more local attention head, and this is more of a global attention head. And you combine the information from all the different attention heads to get mixture of local and global information. Now, what is the advantage of this approach? We have totally gotten rid of positional embeddings, right? So we can train with the 1024 tokens, and when we do inference, all that let's say if we go beyond 1024, what will happen? All that might happen in the worst case is that the token at the 2048 location may not be able to attend a token at a 1024 location. The attention might go to 0. But it won't be seeing any new information. Just attention might go to 0. So it does not completely solve the problem of attending beyond a certain context length, but it allows you to fit more tokens without the perplexity increasing. There won't be any increase in perplexity if you are adding more tokens, right? Because there is no new signal that it has not seen during training. Why does this help? Because there is no extra information that is not seen during training that is being provided, right? And the problem with this is that it still not be able to attend tokens which are very far apart, because the attention between far apart tokens might go to 0 still as you increase the context length. So it will not attend, but the perplexity may not improve, but will also not drop. Okay, so this is where the next solution proposed comes to the picture. So the idea was that, okay, as the number of tokens increase, we still want to keep position embedding. As the number of tokens increase, I still want to be able to attend the tokens that are far away, and that attention value should not drop to 0. So let's interpolate between the positions. What I mean? So interpolation, if you think of the position embeddings, right? You are trained with position embedding of 0, 1, 2. You have trained the model with up to position embedding 1024, right? Now, if you take these position embeddings and you want to create position embedding from 0 to 2048, how would you do it? Very naive thing. You have this position embedding. Let's say you have a position embedding for 0 and 1. That's all you train your model. Now, if I say that no, I want a position embedding for 0, 1, 2, and 3. How would you interpolate between those embeddings and the new set of embeddings that you want? Keyword is interpolation. I want you to think in terms of interpolate, that you have this embedding E0, embedding E1, and I want you to create embedding for E0, E1, E2, and E3. So you can just draw a line between these two embeddings and just put 3 points in between. That you will get 4 segments now. You will basically get now 4 position embeddings. So that idea is what is being what we'll discuss. It's a very simple idea and it works quite well. As I mentioned, in Alibi, the attention heads can have very narrow vision. There are some attention heads that cannot look beyond 2 tokens. There are some attention heads that cannot look beyond 4 tokens. The attention scores drop dramatically, right? So model is effectively, even though you are able to scale to 2048 tokens without dropping perplexity, the model is not looking at those tokens. The model is just ignoring those tokens. So so instead of the model, instead of putting bias in the attention, let's interpret the position embeddings. So you have this, let's say you have this position vector for 0, 1, 2, and 3. And this is what you used during training. And you want to get a new set of position embeddings. What you can do is you can take this position embedding and this position embedding and take the average. This is this is not what is done. We'll talk about what is done. But naively, what you can do is you can take the average of these two to get a position embedding for let's call it position 0.5, and similarly here and here, and you get a bunch of embeddings, right? And now instead of 4 position embeddings, you have 1, 2, 3, 4, 5, 6, 7 position embeddings just by interpolation. But now what we want to do is we want to do it for rotary position embeddings. The idea in rotary position embedding is that you have this vector x. It can be a query vector, it can be a key vector, but you have this vector x, and you want to incorporate the position information. Is adding something, you want to rotate it. And so let's look at this. You have this vector x, x0, x1, xn minus 1 up to xn. Now think of these as a collection of two-dimensional vectors. Okay, you can think that these so this is d minus 1, I should say d minus 1 d. This is a collection of d by 2 two-dimensional vectors, and based on the position of this particular token, so this corresponds to, let's say, token at position 3. Based on this position 3, you want to rotate this vector. So this is right, x0, x1. You want to rotate it in the 2D plane, and you want to rotate each of these in the 2D plane, and you don't want to rotate them equally. You want to, let's say, rotate this much at a much higher frequency and rotate this at a much lower frequency. But each of those frequencies are dependent on the position of this token. So this position is 3. So this is what it looks like. This is your original token. What should I say? Token vector, and this is the angle that you rotate the token while incorporating position. So this, is there any question about this? That rotary position embeddings. It's a very interesting concept. It's very popular. So I would encourage everybody to look at it more. But the idea is that you divide your embedding into two-dimensional vectors and rotate each of those two-dimensional vectors based on the position of the token. Okay. And so the position of the token is 3 here, let's say. Then each of the token will be rotated as a function of 3 now. Okay. So m is 3 here. Okay. Now, if you want to do interpolation for these rotatory position embedding, how would you do it? Earlier we were interpolating between two vectors. Now we don't have vector, we have angles. How do we interpolate between these two angles? Anybody? Any idea? First of all, think of what rotary position embeddings are doing. They're just rotating your embedding vector by certain angle, right? So if you want to interpolate, how would you do it? Correct. You can simply, that's what exactly this paper does. It just says that, okay, since the rotary position embeddings are rotating the embedding vectors, let me divide this angle into the number of position vectors I want to create. So if I have 1000 position vectors and I want to create 4000 position vectors, what I will do is I will just take this angle and divide it into 4 parts, and each of the new vectors that I will get will be a new position vector. So by the way, this is the expression that is written here is just a complex valued representation of what this operation is trying to do. So as I mentioned, you have divided into two-dimensional vectors. So this is the you can write it as a complex number, and this the rotation vectors can be written in this form as e to the power I m theta. You can also write it in matrix form. You can write it in this is a more writing it in complex form is more what should I say better way of representing what this operation is doing. If you have the query, as I mentioned, x can be a query or a key vector. If you have the query vector, you can also write the query. If you have to rotate the query vector for the token at time step m, you can write it in this form. So here q is basically your q0, q1, qm minus 1, and qm. And similarly for the key, you can compute the rotated representation of the key, and you can write it as well. This is so basically key vector for token at time step n, and then you can compute the inner product. Basically the attention is a function of the inner product between these two, and the inner product looks something like this. You have this original query and original key vector, and this is the difference of m minus n is the difference in position, and you get a rotation So you get a rotation which is dependent on how difference in position of the two tokens. So if the two tokens are more far apart, there's a much more rotation, and if the two tokens are closer, there's a smaller rotation of the of this vector of this yeah. So the attention is a function of the product between the query vector and the key vector, and the angle between the position embeddings, which is a function of the difference in position. And let's call this quantity the inner product between the query and key vector as Hj. So it's a function of Hj and the difference in position. And if you look at this vector, this you can quickly see that this quantity is, if you look at the absolute value of this quantity, is going to be bounded by the maximum value that this Hj can take times how many times I'm summing this up, and this e to the power im, and this is anyway constant. So this, you get an upper bound to how much the attention scores can vary, right? And this is going to be important because we derive that, okay, when I do interpolation, how much the attention scores change compared to what the attention scores that I get. Okay, so as I mentioned earlier, that when you're doing interpolation, all you have to do is, so this was your original this is the original rotated representation after adding position information, the blue one, original rotated representation, and the red one is the interpolated rotated representation. So when you are doing interpolating, you are just dividing the angle between the rotated representation and the original representation into some parts, and that gives you the interpolated representation. And here the original number of tokens, so L is the original number of tokens that you trained on, and L dash is the new number of tokens that you want to do inference on for inference. And here we are assuming that L by L dash is 2, so you just divide the original angle that you got into two parts, and you can write this in this form, that the new position embedding f dash after interpolation is the original position embedding of the token at location ml by l dash. Okay, so we had trained the network with the position embeddings where the value of m minus n ranged from, let's say, in this belong to 0 to, let's say, 1024, and now we want to do interpolation, and now we interpolate, and now these values can be fractional. So when you do the attention scores, how does the how much change does it happen to the attention score? I mean, do they go very very widely, or do they remain almost the same? And that is important, because if the attention scores change drastically, that means the model will not be able to do inference correctly. So when I computed these, when we compute these interpolated vectors, does the attention scores vary very widely or not? And there's a theorem in the paper which shows that the attention scores don't change that drastically. In fact, we derived a value for the attention score, right? That attention score is less than equal to d by 2 times max over jhj. So this quantity with 2, we derived earlier, and what this paper shows is that interpolation ensures that your attention values don't change very drastically. You don't need to go to the don't need to go through the derivation, but it's just to know that the attention scores don't change very drastically. If the attention scores before interpolation had some let's say had some value, and after interpolation it becomes very widely, that means the models, because the attention, your model behavior, the embeddings that you compute, it depends on the attention values, right? Everything is a function of the attention value. So that means the model behavior is going to change, models outputs are going to change, models embedding, everything will change, and so basically your model will not be able to perform correctly. In practice, even when we do this interpolation, even though the attention values don't change much, fine tuning is required, and the reason is that you can think of is that earlier what the model thought of as the token at a distance of 1, now that same position embedding is used for token at a distance of 2. So the model, you still want to make sure that the model understands that, okay, what was earlier 1 for you, now it has become 2. So you still require some fine tuning, and you have to fine tune it on a fraction of examples, and then it starts behaving well. So this is a figure which shows that the perplexity earlier, which blew up, ignore the red and ignore the yellow lines, and blue is the perplexity for position interpolation, and the perplexity decreases as you increase the number of tokens, as is what we would expect, right? In general, that if you add more tokens, the more knowledge it has, the perplexity should decrease. And this was linear interpolation, where you just take the angle and divide it into equal parts. People have also looked at NTK inspired interpolations, where you try to not divide all the angles equally, but use some non-linear divisions. Okay, we will not discuss about them, but they have also become popular nowadays. Okay, so finally, we have talked so far about how we can take these models that are trained for short context and use them for long context. What we want to see now is that, does it even help that if I take these long context models and give a lot of data to them, can they do reasoning over these long context at all or not? So, and that's the lost in the middle paper. And the idea of this paper is, and so if this is the takeaway from the paper, that if you give a lot of documents to the model is not going to look at all the documents equally. The model is going to focus on some documents at some position. Model is going to focus at some positions and will ignore all the other positions. So although you are creating this large LLMs which can look at large context windows, they are not actually giving equal attention to all the positions. They will attend on some positions, and specifically they will attend on the starting. Okay, first of all, if you have to think, and if I ask you that what positions will these long context models be able to attend to, and what positions will these long context models not be able to attend to, can you think which information might get used in the long context element, which information will not get used? The information that is given to the LLM at the beginning and end gets used much more than the information that is given in the middle. And as I mentioned, the idea of idea of this work is to find out if the model is paying equal attention to all the positions, or is it focusing only at few positions. Okay, and the way they do is they took a question and they took a gold document for the question. So the gold document means it contains the answer. Okay, and they added a bunch of distractor documents which do not contain the answer, but they are also very similar to the question in the sense that they are obtained with from a retriever. Okay, and when you feed these distractor documents and gold documents along with the question, and now you ask the LLM to answer the question, and you vary the number of distractor documents and vary the position of the gold document with respect to the distractor documents. So this is an example of a question. The question is, who got the first Nobel Prize in physics? And you have a bunch of, this is the gold document. The first Nobel Prize was awarded to Wilhelm Conrad Röntgen, and you have a bunch of distractor documents which are also talking about Nobel Prize but do not have the answer. So when you do that, this is what was observed, that if you retrieve 10 documents, you have a total of 10 documents and one gold document. If the position of the gold document is, if you put the gold document at the first position, all these models, Claude, GPT 3.5, all these models give decent performance. But if you put the gold document at the fifth position, the performance of all these different models drop. Here the performance you can measure as the accuracy of the answer that is generated. And if you put the gold document at the last position, the performance improves somewhat compared to the middle. Okay, so the worst point that is this is if you put the gold document at the fifth position, you get the worst performance. So which is interesting, and they decided to increase the number of documents, and this is the figure that they got, that if you put the gold document at the first position, again the performance was best, but for 5th, 10th and 15th position, the performance of the LLM dropped if you put the gold document in these positions. And you can further increase the number of documents to 30, and you again see a similar U-shaped curve where if the document is in the middle of the LLM, the model is not able to find the correct document. It's not able to answer using the correct document. and they varied the model architecture. The idea is that maybe possible that these causal attention masks where you are attending only on the previous tokens is causing this problem. So if you use bidirectional models, the problem for less 10 documents is somewhat lesser, because the green is the plan T5 and red is the plan UL2. So the drop for the fifth document is not that huge, but there is still a drop. But as you increase the number of documents, this trend is same as for the unidirectional model, the causal LMs. That as soon as you put the goal document somewhere within, somewhere in the center of the LLM, the model is not able to attend to those goal documents to generate the answer. And this problem remains whether you use an instruction tuned model or you use a pre-trained model. It does not make a lot of difference. And this is the retriever recall versus model performance. So basically the idea is that if the model is not able to attend on documents that are in the middle, if you, let's say, even if you retrieve a lot of documents, the model may not be able to look at it. So retrieving more documents does not help. The performance does not improve as you retrieve more documents. Although the retriever performance, this is the retriever performance, and this improves. You are able to retrieve, find the correct document with a much high probability, but the performance of the LLM does not improve. Okay, we have come to the last slide now, but we have looked at some ways to increase the context window of LLM. We have looked at ways where you train on a smaller context and do inference on a longer context. But we also saw that even though you are able to incorporate have this much long context, model might ignore the information that is in the middle of the context window. Okay.